Now in this session we are going to show that the centripetal acceleration A is equal to v squared over r, where our A is the centripetal acceleration, then v is the linear speed, r is the radius of our circular path. Recall we said this acceleration is called a centripetal acceleration because it is in the same direction as the centripetal force, and yet the centripetal force acts towards the center of the circular path, and therefore we call this acceleration centripetal acceleration, since it is towards the center. Now considering a particle moving with a constant speed v along an arc N or P, let's call this point the center of the circular path, we call it Z. If we connected the point Z to N and then Z to P, and we call this angle theta, this is equal to this angle, so it is also theta. Now if we draw a horizontal line, it would make an angle theta with the direction of the particle at point N. The same applies to point P. If we draw a horizontal line, it would make an angle theta with the direction of the particle at that point. This is the radius of the circular path, r. Now the horizontal component of the velocity at N is v cos theta, and the horizontal component at point P is still v cos theta. The vertical component, so we've realized that the horizontal component is in the same direction at all these 2 points, at both point N and point P. Now at point N, the vertical velocity is v sine theta. At point P, so at point P, our vertical velocity is v sine theta. Okay, so if we consider the horizontal motion, horizontally, the horizontal acceleration of the particle will be the change in the velocity over the time. This velocity is the horizontal velocity, but the change in the horizontal velocity will be v cos theta, which is the final velocity, minus the initial velocity v cos theta, and this will give us 0. Therefore, the horizontal acceleration is 0 over t, which is 0. So our horizontal component of the acceleration is therefore 0. If we take the vertical component of the acceleration to be the change in the vertical velocity over time, but the change in the vertical velocity is the final velocity at point P, which is v sine theta minus the horizontal component. We should take note of the direction, minus the vertical component at point N. So this is minus v sine theta. So the minus and the minus becomes positive. And this gives us 2v sine theta. Therefore, our vertical acceleration is equal to the change in the velocity, which is 2v sine theta over time. But the time is equal to the distance covered by our particle, which is the arc length, NOP, divided by the velocity. Now, the arc length, NOP, is equal to, let's go back and see, we are supposed to get the angle times the radius of the circular path. So the angle, we are having theta plus theta giving us 2 theta. So the total angle NZP is 2 theta. So we have 2 theta times r, which is the radius of the circular path. Therefore, our t is equal to 2 theta r divided by the velocity v. This implies that our vertical acceleration is equal to 2v sine theta divided by the time, which is 2 theta r over v. This will give us, this comes up. So considering the laws of multiplying fractions, this is the same as multiplying 2v sine theta times v over 2 theta r. So the 2 and this cancels. This v and this v will give us v squared, implying that our acceleration is now equal to, we have v squared over r, then this is times sine theta over theta. So we have said our vertical acceleration is equal to v squared over r times sine theta over theta. In the limits, as sine theta over theta, as we limit sine theta divided by theta, with theta tending to 0, so it will give us 1, implying that our acceleration is equal to v squared over r times 1, and this is the same as v squared over r. So generally, our acceleration, our centripetal acceleration A is equal to v squared over r for any particle moving in a circular path.